Hello, so in this video we're going to cover how to implement the neural network and set up our agent's environment, letting it see the world, getting a state space, which we learned in previous videos. Remember, the state space is basically observing the environment. It's one of our first steps in DQN agents. In this flowchart, the environment is passed into the Q network, and this will output which action to take based on the current environment, and obviously based on trained experiences. So we're going to be implementing this get state. We're going to set up the neural network that we're going to pass the states in right here. We pass the state into the input layer. It goes through the trained network and it will maybe output like a movement it should take. So like maybe it should move right. All right, so let's get started. So hopefully you guys from the last video have this exact code set up. We're going to be changing a lot, and yeah, so now we're going to start thinking of what needs to be in the agent state space. So here we have the raycasts already. We already know those all are going to need to be given to the agent. So that's already 8. We're also going to need the x and y to the nearest coin. So that's 9. And then this is 10. We're also going to need the x and y of the agent. So that's 11. This is 12. And then maybe we also need to give it if it's on the ground or not. So we need to let it know if it can jump. So maybe on floor. So on floor is given to the state, and that's 13 now. So overall, the state size of this agent is going to be 13. This means we're going to input 13 values into the neural network to get a predicted Q value for each action. So for a basic visualization of the neural network architecture, we're going to have basically, remember we talked about the state size. It's going to need to be 13. So we're going to have 13 input nodes. And then for our architecture, we're going to do 64. It's going to be huge, but just ignore it for now. And then 3 output nodes. So like right, left, and jump. So when we pass in the state into this neural network, these output nodes will output an action like left or right, which one's the best to take from the state. So basically in DQN, we're taking this environment and we're extracting the state from it. So here's the environment of the game, and we're going to extract the state from it. So we're going to take things like position X, Y, this is a coin, all the raycasts, and is on floor. And this is all going to be pulled from this function called getState that we're going to implement right now. So we're going to start with a function called getState, and this is basically going to return an array of our 13 values. So we're going to have like distance to coin dot x. Make sure to put a comma. Distance to coin dot y. Position dot x. Position dot y. And then vision. For vision, remember we made this vision object. So each time we call getState, we can just update vision, and then we can just pull. We can get the values for each raycast. So like raycast underscore up. And for this, look at, you can have a default value in this get function. So if, let's say this value is not in the vision, let's just default it to like a value 1000. So we need to do this for all the vision raycasts. So once you've written all the raycasts, we now just want basically a integer to represent if we're on the floor, if the agent is on floor. And we already have a pre-built function for this. So we'll just do this. So now we need to implement a way to get the nearest coin, so the agent knows where the nearest coin is. And I actually attached a a script down below, just a little function to actually calculate the nearest coin position based on the agent's position. So just copy and paste this in, and we're going to need collectibles. So let's go up to the ready function, or define a global variable collectibles. Go into the ready function and call collectibles equals get tree dot get nodes in group, and then collectible. That just collects all the coins, and this function gets the nearest coin. So then now to calculate the distance to the coin, we can just do a formula in the get state, like distance to coin equals just coin get nearest coin position, and we subtract this by the agent's position, and there we go. That should calculate the nearest coin, like its distance, both x and y, and then we can extract x and y by using .x, .y. And this is our state function. And actually this is wrong. This should be position. I don't know how this changed, but position.x, position.y. And this is what you should see in the get state function. So we're going to now use this to pass into the neural network, and anytime we need it, we just call get state. This is going to be useful for training the agent and predicting what moves to take from a specific state. So we'll pass these values into the neural network, and the neural network will find patterns based on previous experiences to basically decide what move is best to take from these values. All right, so next in this DQN player code, we're going to initialize the neural network. So in previous videos, you should have already installed the neural network. If not, you can just go into asset lib, look up neural network, and just go here and just download this. And it should save these files into your code or into your project. And now we're going to just initialize DQN and neural network stuff. So let's actually make a comment section, 3 bars. We can do DQN setup. So there's a few things we're going to need to define. In the previous video, we learned there was going to be a Q network, which we can define using this. You don't need to really know this, since this is just syntax for the neural network architecture we're using. So we're going to have a Q network with, remember, 13 input nodes, and just for now we're going to do these hidden layers. These are going to capture the patterns, and then we need the output layer, which is what actions are possible. So we're going to have 3 actions possible, and then just for now we're just going to do false. This is just a default value. And then we also need a target network, which we'll get into later, but it's basically just going to be a copy of this. So just copy that. We're going to need to define epsilon, which is how often the agent should take random movements. So we're going to start with 80% chance it takes a random movement versus and 20% chance to take a best policy movement. We're going to have gamma, which basically is just how much the agent is going to prioritize long-term rewards or short-term rewards. We're just going to leave this here. You don't really need to worry about it right now. Remember, we need a replay buffer to save experiences, which is just a basic list. So just have a basic list. We need a max buffer size to determine how many experiences we should save at a given time before we start removing experiences. So we'll just set this to 5,000 for now. we're going to need a batch size, which is each time we train the agent, how many experiences are we going to use each time to train the agent? Because like we can't train on 5,000 experiences each time because that would be too much computation. So we need to do it in batches. So we'll do it in batches of 64. How often should we update the target network? This is just for stability. The target network is basically just an exact copy of the Q network, but we periodically update it. For when the Q network gets good, we'll update the target network. So let's just have this at like 1,000. We need a step counter to count how many times or what step we're on. We're going to need train frequency for how often to train the network. These you don't really need to worry about right now. Just train counter, start at 0. All right, so now let's, in this ready function, we're basically going to be completely restarting. We're going to initialize the neural networks. So just copy what I have, and initially we just need to configure Q network and target network. So now we're going to set up some stuff. I don't want to go too in depth because it can get confusing for some people, but we're just going to define these hyperparameters and settings on our neural network that are going to aid learning and like determine how it works. So kind of just copy what I have. And then now we're just going to basically do this again on the target network because they're basically copies. And just to make sure no errors happen, we're going to assign the target network the same weights as the Q network. And actually we can just completely remove this initialize function. We actually don't need it anymore. Although for level, let's actually make level equals get parent, put it in that ready function, and we don't need this anymore. And we're going to start making the training loop in the next video. So thank you for watching, and any questions, put it in the comment section, or we'll also have a blog post where you can read some possible errors or failures that you might have, and we'll try to solve them. So thank you for watching, and see you in the next video.